Well, welcome. We've been clouded out again. Last week it was rain. Today it's high cloud cover everywhere. But we're gonna, keep muddling through. I still apologize for our computer difficulties last week, but I hope everybody had an opportunity to download Stellarium and play with it. Take a particular star or nebula and turn the clock on and watch it traverse the night sky. That's one of the fun things you can do with Stellarium, is see where everything's going to go. So tonight, if we have this working, tonight we're going to talk about basic astrophotography. By basic, I'm referring to photography of stars, nebula, planets, galaxies, in which we're just taking a single shot. And the objective is to try and, get locations and relative, spacing between stars and objects in the night sky. Here's our roadmap again. This is Module 6. And we hope next week we'll be at Chamberlain, but we are still somewhat, we're a captive of the weather. So tonight's agenda, previously we learned that observability of an object in the night sky requires a combination of how big it is, arc minutes, and also the visual brightness. For planets, the moon, nebula, and a lot of the galaxies, the issue is how big it is, but with stars in particular, the main issue is their visual brightness. We learned earlier in the second module that some of the astronomical objects you can see with just the naked eye. You don't need binoculars or a telescope. Now, does anybody remember what that magic breakpoint was in visual magnitude that you can see with your eye? Bingo. See, you're learning something, guys, gals. Yeah, well, the thing to remember is if you look up a star or a stellar object, they typically are noting visual magnitude. When you look at that number, it'll tell you, oh, I can see this with the naked eye. Or, that's something that Hubble telescope will have to resolve. We had a talk a few weeks back about the different types of optical devices for viewing the night sky. We started with binoculars, various types of telescopes. And, basically you can spend almost as much money as you want on a telescope. If you got $1 million, there are places that'll sell you one for $1 million. But, you may not need a $1 million telescope. We did not get a chance to go to Chamberlain yet, so I'm going to pass that one by. Last week, we attempted to try out observation planning tools. That was the Telescopius website, or the Telescopius program, that basically will show you what objects are available in the night sky at your location with equipment that you might have. And we also attempted to show that Stellarium, which is another popular observation planning tool, you can put in your own personal viewing location. You can put in the equipment that you're going to be using, and it will, both of those programs will generate simulated pictures of what you could see. And that's really helpful because it avoids wasting your time. You cannot see something that Hubble telescope resolved that's, 300 billion light years away. Don't even bother. Let Hubble and James Webb deal with that. Tonight, we're going to cover the simple hooking up of a camera to a telescope. And I've actually brought in a telescope and some objects for, how you actually accomplish the hookup. So one of the key reasons, I have had a lot of people in the DAS say, why are we putting cameras on telescopes? Why any kind of astrophotography? Well, the answer is the history. A long, long time ago, like in the period of Galileo and the various early observers, the way they recorded what they saw was with hand-drawn figures. And when they wanted to communicate, maybe by writing a letter, like, I understand there were letters between Newton and Kepler and things like that, they were doing hand-drawn sketches of what they saw through a telescope. And, here we are in the 21st century. Maybe it's a little quicker just to snap a picture of what you're seeing through a telescope. So here's my great picture of one of our great leaders. In Galileo's time, everything was done via hand-drawn figures. If they went to publish something or put it in a book, it all started off with a hand-drawn sketch. This is an interesting, this is an image that Galileo produced of his observations of the moon. It's all hand-drawn. And this is from, gosh, I think it's got to be 1600s. I don't have the exact date. This came from a publication called Sidereus Nuncius, the Starry Messenger. I'm going to show you a comparison of his sketches, his hand-drawn sketches, with an actual photograph taken by NASA. Here's his sketch, and here's the a detailed image taken by NASA with good cameras. They're within some artistic license. You can tell that it's the moon. The sizes of some of the crater areas are obviously different, but you get the idea that hand-drawn sketches, what do we call it? I guess it's artistic license. He was writing a publication, said, look what I saw on the moon the other night. His hand-drawn sketches, though, in some regards, are very accurate. And I've got an excerpt from a paper where somebody took stellarium and they compared it, knowing the exact dates that Galileo made the observation. You see, I'm trying to remember how to use the flash. Yeah, there it is. This is a stellarium picture, and this was Galileo's hand-drawn picture. And there are dates and times when the images were actually captured. But when you look at these things, he captured what was actually going on in a hand-drawn sketch. I thought this was an amazing paper, that somebody took the time to do this. But it came from a paper called The Accuracy of Galileo's Observation and the Early Search for Stellar Parallax. But at any rate, at that time, you didn't have cameras. The way they recorded and studied the position of stars and planets was all done with hand-drawn sketches. And you can see when you look at them, there's a little bit of inaccuracy. You get the idea what they were doing here, but the exact separations, between this and that are, artistic license. To really capture detail, you need something like a camera taking an actual picture. As we move into the photography era, daguerreotypes and all of that kind of stuff, the earliest ways they captured stellar images was via glass plates. From the 1880s through 1989, astrophotography technique, the main thing that was done, they were using glass plates. I don't even know how you develop a glass plate, but they've got a pile of them, as I understand, at Chamberlain Observatory. There is a collection from the last century. There is a very important collection held at the Harvard College Observatory. They've got 500,000 plates with information about stars on them. The data was collected through telescopes, and the observations that they made were all recorded in very great detail. One of the things, if you read a little bit of history of astronomy, the chief astronomers at Harvard University, well, let's put it mildly, they were sexist. They hired women to come in and do what the men didn't want to do, which was to look at the plates, take measurements of how far this object is from that one, and what's the relative angle between these bodies. They literally hired women at a fairly low wage to come in and look at these plates and form conclusions. They may not have listened to them, but if you go back into the history of women astronomers, some of them actually were observing stuff that the men weren't interested in. And I thought that was kind of an interesting story. I tell that to my daughters. This is a fragment of the Andromeda glass plate taken by Edwin Hubble. Now I will tell you that you can see that that's Andromeda, and the big dot to the side I'm presuming is M110. But that's a little hard to read, but that was what they were doing. So now, science moves forward. We get a transition from glass plates to film photography, and now we're using CCD cameras. The photographs, one of the reasons they're very important, if you know the time that you took the photograph, they measure angular and luminous relationships between the stars. You can see the bright ones versus the ones that aren't so bright. You get their orientation. You know where you were shooting from. They capture all of that in one photograph. And that's what's really driving the use of hooking a camera onto a telescope. Another feature is that modern digital cameras allow an almost instantaneous review. If I took a glass plate and made an image of a galaxy, like when in Hubble's time, where he's trying to figure out the rate the galaxies are spreading apart, and he fudged it. He didn't have enough developer on the glass plate, or somebody dropped the plate. They aren't going to be able to recognize it until they've developed it. Right now, our modern cameras allow an instantaneous review. You can go back and look at it and say, oh, I don't like that image, it's fuzzy, or a crow flew in front of my telescope. But you've got the ability to quickly reshoot as needed. The other thing that you get with a camera is, if you've set your camera up properly, it tells you the exact minute that the picture was taken. So you've got a record of where, when, and what you saw. Additionally, you can capture color images, unlike the old glass plates that were kind of white, gray, and black. So a little bit about the optical theory of cameras and lenses. The field of view is probably the most important feature we're interested in. One of the problems you get sometimes is you want to take an image of a distant object, And I have had this personally happen to me, and I get it zeroed in, I got the location down, I take the picture, and then I realize, oh my God, that actual, arc minutes is way, way bigger than the field of view of my camera and lens system. There is a formula. This came from the Celestron website, their help section, which says that the field of view is approximately, and this is the formula, where D is the effective diameter of your sensor in millimeters, and L is the focal length converted to inches. I have no idea why they don't just put it all in millimeters, but at any rate, this is off the Celestron site. Basically, the formula shows that a longer focal length is going to give you a narrower field of view. And if you're a photographer, you'd say, yeah, but I knew that already. Really, all we're doing by putting a camera on the end of a telescope is we've just made a really long lens, is all that we've really done. But basically, the longer the focal length, the narrower your field of view, that what you can see in an image you capture. And I'm going to try this out with several astronomical objects. Basic astrophotography. Tonight we're going to look at solar imaging techniques, lunar imaging techniques, planet and constellation imaging, and Milky Way imaging techniques. So we're going to cover 4 things. Now, the one thing that is common about all of these is we can do that in a single camera shot. We don't need an expensive tracking mount or, telescope like Chamberlain. Solar imaging. Recall in Module 1, we pointed out that the size, the sun is about 30 arc minutes, which is a half a degree. The full moon is also about 30 arc minutes. Now the difference in the moon is the moon close up to the Earth or is it farther out? When we get a full eclipse, the moon is farther out and hence it covers the sun. When it's closer in, it's not a full eclipse, it's what they call an annular eclipse. In other words, as the moon passes in front of the sun, there's a ring around it, an annulus ring. We talked about the size of some of the things. Visibility, which is, sun is hugely bright. The full moon is really bright. Jupiter is, you can see it. Vega is about 0 on the scale, and here's our limit of what you can view with the naked eye. Everybody remember those from the first session? What can be observed with just a camera? One of the things that's very fun to do with a telescope or a camera is to look at sunspots. If you've got the right setup and the settings, and I'll get to that in a bit, you can see the sunspots, you can see coronas and flares and all that good stuff on the sun. You can also see what are called solar prominences. These are the pink and purple bands that come off from they look like a column jetting out from the sun. And of course, annular and total solar eclipses. Characteristic of light from the sun. This is a spectral irradiance. This is in the units of watts per square meter, and then per nanometers of wavelength. One of the things you see here is that at the distance we are from the sun, because we're up at high altitude, we actually get an energy density of 1360 watts per square meter. Think about what that is. What's the power of your microwave oven? Anybody got a number for that? It's about 1,200. Of course, it's not concentrated in a meter, but that gives you an idea that the sun at our altitude could really do serious damage to your eyes if unprotected. If we go down to sea level, however, because of the additional air, it cuts the power of the sun down a bit. But at any rate, this shows the range of visible light right here. This is what we can see easily. Over here is the UV. This is the stuff that gives you a sunburn when you go to Vail on the weekends in the spring. And down here you've got the infrared. This is basically a lot of heating. But at any rate, this is what the power, the power distribution of the sunlight is. Solar filters. Given that we in Denver area are at this value of 1,300 watts per square centimeter, you've got to filter it. There are two ways of doing it if you're trying to use a camera. One is to what they call stacking neutral density filters. In other words, you take a couple of filters, you stack them all together so they make up about 16 f-stops. How many photographers in here? Any? One? I see one or two. At any rate, this is an example of how you can put two 8-stop filters together and make one that's about 16. There are also commercial telescope or camera solar filters. And I've actually brought one with me. I'm gonna stand up, get some exercise. Bring it. Oh, you're gonna grab it? Thank you. Thank you. This is a commercially made filter for either a telescope or a large lens. And it basically has a big ring and it's got Velcro straps that you put around it. And when we take a break, I'll show you I have mounted this filter on that telescope in the back so you can see what we're talking about. So that's an example of a commercial filter device. This is what it looks like. But we also have the ability to make your own. You can buy this safety filtering material like so. Places like B&H Photography in New York, and I'm guessing that Mile High Astronomy here in Denver, they carry these types of products for protecting your eyes and your equipment. This is the filter material. It is safety approved. Like don't go out without it. What I did was I manufactured my own by taking a sheet of the material. I cut two cardboard rings, glued it, and this is what it looks like when mounted on a camera. I've actually got this rig laying on a table in the back, and we'll take a look at it a little bit later. But the advantage of this being rigged like this, particularly for shooting an eclipse, is that while the sun is very bright, it's filtered, but I can pop the lens hood off when I get to totality. It's very quick to take off. That's the advantage. But you can make this at home with one of these that I think they're $4 or $5 to buy. Field of view of the sun. Previously, I showed you a slide that it's about 30 arc minutes. So what I'm going to show you is I have a Nikon D5300. The sensor on the camera, based on the specs, is 23.5 by 15.6 millimeters. Can I image the camera with a 300 millimeter, can I image the sun with just a 300 millimeter lens? And I'm going to convert that to inches there. There's my 300, turns out to be 11.81 inches. The field of view works out to be 178. In other words, it's pretty big. The sun will only fill up about 1/6 of that frame. 30 arc minutes versus 178. So what I want to do is actually put something in and get a little bit bigger of a focal length. So how about if I now do what I did, which was to put what's called a doubler in the lens system, taking it out to 600 millimeters, 23.62 inches. It brings it down a little bit more than, well, a little bit less than half. But basically with that rig, the sun will take up about 1/3 of the frame. If I wanted to have a total picture of the sun, you can see that I'd need to get a bigger and bigger focal length on my lens system. Does that make sense? But the whole thing I'm trying to make you aware of is if you want to get the field of view matching the object you're trying to shoot, what you're playing with most of the time is the focal length of the lens. You can't change your sensor diameter, your sensor numbers. Camera setup for solar imaging. To do it properly, you can't hold a camera up and take a shot. You'll jiggle it too much. You need a sturdy tripod with an external shutter release. One of the things I would do is, 300, 600 millimeter lens, turn off all of the camera whiz-bang features. Like there's a stabilization for motion stabilization. Maybe you'd use that if you're riding in a train and trying to take pictures out of a train window, but you don't need it if you're trying to focus and shoot the sun. I would pre-focus the camera on infinity. Don't use the autofocus feature. The reason is it's going to go in and out, may not ever reach solution. So what you do is take the camera with the lens hood off and focus at something like a tree, a mile away across the valley. Get it in perfect focus there. And then one of the things I typically do with my cameras when I'm doing this, I take some whiteout. How many people remember whiteout? The secretaries loved it. You could white out something that was screwed up on a Selectric typewriter. Well, anyway, I took some white out, and after I got it focused on infinity, I just put a little line across it so I can very quickly get to infinity on the manual focus. When you're shooting the sun, you want the white balance set, depending on your camera, it'll either be sunny or if you're using temperature, typically 5500 Kelvin. That depends on your camera. On a Nikon, you can set it using Kelvin. I believe other cameras use things like sunny and tantalum and street lights. They've got, more descriptive names, like on the Canons, I guess. You want manual shooting control. What you want to do is, like I say, turn off all the automatic features. This sounds like, oh God, are we going to get anything without all those wonderful automatic whiz-bang features on the camera? what you really want is just a real plain, simple, old-fashioned camera with all the whiz-bangs turned off. I usually save images in RAW format because that captures a maximum amount of image data. And that's what you're trying to do. Camera setup. The ISO settings may be camera and lens and filter dependent. I don't know what type of camera you might want to try playing around with. There is what photographers call the Sunny 16 rule. And it's one of those things I have no idea how it was derived, but everybody seems to know about it. It's the best starting point for shooting at the sun. The Sunny 16 rule states you start with an f-stop, your aperture setting, and you set the shutter speed to be 1 over the ISO, the sensitivity setting on the lens. So 1 over the setting. So there's some examples. f16, ISO 1 or 200, and you'd be doing something like this, 1/200th of a second exposure. And believe it or not, that dumb thing, it works pretty damn good. If I had a different ISO, like ISO 100, I would be looking at 1/100th of a second exposure. This is just a very, this is just a very simple way to get it set up to shoot the sun. Any question? By the way, you don't need to photograph these. We've got the PDF versions of the whole thing are online, so you can download them afterwards. But my intent here is to give you some real quick starting rules. Solar imaging. This is an example. Before the eclipse, I went out on my deck last March before we took off for Arkansas, and I was out just shooting sunspots. And you can get pretty good just with a very simple setup. This was f16, ISO 200, 1/200th of a second exposure. This was a shot I took down in Arkansas during the total eclipse. And you can see along the sides, we got all of the corona, these pink things. These are the solar prominences. They are like columns of gas and plasma coming out. But this was actually a relatively easy shot to take. You can do this at home. I mentioned what the settings were. Now I'm going to jump to how do you take a single picture of the moon. I mentioned earlier, the moon is a pretty darn bright object. You may not think of it, but it is. Here's from Module 1. We've got the size is about the same diameter as the sun. Its luminosity its visual magnitude is a whole bunch less, but it's still quite bright. It's much brighter than a lot of the stars and Jupiter and things like that. The choice of the lens focal length will be similar to that for the field of view when shooting the sun. But obviously the visual brightness is significantly less than the sun. Camera setup, it's going to be different. Again, you want a sturdy tripod so you're not jiggling it while you're holding it. You also want to have an external shutter release so you don't touch the camera, you're just clicking something remotely. Again, I would turn the visual stabilization off. Pre-focus it on infinity using the same approach I described for the sun. Look at some extreme distant object like a tree in a ridge line a mile away, and get that in focus and you'll be fine. Turn off the autofocus. White balance will be different. I typically would use on a Nikon camera about 3800 Kelvin. I believe, I may be wrong because I don't own any Canon cameras. I had one about 30 years ago, but now I shoot Nikon. I think it's called titanium. That's kind of a white and blue light is what it's being set up for. Again, manual shooting control. Turn off all external, whiz-bang features like auto ISO and things like that. Save it in RAW format. The setup. Again, I'll give a caution that the ISO settings may be camera dependent on what you've got rigged, because the moon is a lot less brighter than the sun. You're going to have to use a much wider aperture. In other words, you're going to have to open up your f-stop quite a bit. I have successfully shot it with f8, which is, way open. And then ISO 200, and I started with 1/200th of an exposure time. I got this image. It actually looks blurry in the image on the screen, but I think Galileo would be happy with this picture. Okay, this was an example. I went up to, what's the park? Mount Falcon Park in January of 2019. And I shot the entire sequence of the, what was it called? It was called a super wolf moon lunar eclipse. Quite a title. Okay, planet and constellation imaging. Any questions about the differences between moon and sun shooting? None? Okay, Jupiter, the lumen, or the major, how would I characterize? Excuse me, the visual magnitude is again a whole bunch lower than you saw with the moon, but it's still brighter than some of the stars you would see out there, like Vega. The thing that you're dealing with now is that the planetary and star targets are significantly smaller and they are dimmer than when you are shooting the moon. So capturing the images requires more magnification and a higher ISO. ISO is basically dealing with the reduced brightness. You're going to be raising the ISO. Again, steady tripod with an external shutter release so you're not jiggling your camera while you go to shoot. I'd use either a 600 millimeter lens or a telescope. And when we take a break, I've got a telescope set up back there that I'll show you how you rig a camera with a telescope. Again, you're going to pre-focus the camera lens or telescope on infinity. And one of the things I'll show you on my telescope back there is I pre-focus the telescope on infinity the same way. I look at a tree or a house that's a couple miles away across the valley. And what I did on my telescope was I took a black magic marker, and when I got the thing in daylight, focused on infinity by looking at a tree a long way away, I took the black magic marker and I circled the extension tube on the telescope. What that means is that I can go out and not have to deal with that every time I set up my telescope. And it's a handy, handy trick. Again, turn off autofocus, virtual stabilization, titanium or 3800 degree Kelvin, depending on the camera. Manual shooting control, again, turn off all the other whiz-bang features and save them to raw format. Okay, the deal on connecting a camera directly to the telescope goes through a system that involves what's called a T-ring, and I will show you that in the back of the room. A Barlow lens, typically to give you the focal point where you want it, and then something that puts you right into the optical tube assembly of the telescope. This is a blown up diagram showing the pieces. This part right here is what's called the T-ring, and different T-rings are made for different cameras. If you have a Nikon F-mount, you can go to B&H Photography and say, I want a Nikon F-mount T-ring. There is an adapter that it fits onto. By the way, this will literally plugs right into your camera body. It's made to do that. The Barlow is right inside here, and this piece right here is what goes right into the optical tube assembly of your telescope. And I will demonstrate that in the back of the room when we take a break. This is a picture of my personal telescope set up on my bedroom deck. And there's the camera. There's that adapter piece I had right there. There is the optical tube assembly. And if you look closely right here, you'll see my little black ring around the tube, marking where infinity is focused at. So this tube has a 900 millimeter focal length. It's got an extension tube, and here's all the gear mounted to it. And I'll show you that, how it all fits together in the back of the room. Now this rig right here could do more, but I'm discussing tonight how to use it to take single photographs of stars, planets, moon, sun. Set up for planets and constellations. Okay, one of the key problems when you want to get something that's dimmer, you want to get more light getting into your camera system. And one of the ways to do that is a long exposure. But if you do that, you're going to come up against the fact that the Earth is rotating 15 degrees every hour, or 1/4 of a degree every minute. So if you try and take a 10-minute photograph to try and expose a dim planet, guess what? It's going to be all smeared because of the rotation of the Earth. And so what I'm talking about tonight is how to take single shots. Long exposures are going to get streaked. So how do we deal with that? Well, there's another one of these magic photographer secret formulas. It's called the rule of 500. None of you, no, people haven't heard of it. Some people nodding maybe. But basically, the rule of 500 states that the maximum exposure time in seconds has to be less than 500 divided by the focal length of your optical system in millimeters. And it's amazing. This thing really works. If you hold your exposure time to this limit, you see dots instead of dashes, which is what you're trying to do. So example, if I have a 300 millimeter lens, the maximum exposure time I can use is about 1.6 seconds. I was talking with someone that years ago, in my driveway, I was shooting Andromeda late one night. And what I did was I had my camera rigged with basically to go click, click, click every 1.6 seconds. So every individual image was less than the limit that would make a dash versus a distinct dot. But then, of course, when I get done, I got to take hundreds and hundreds of these images and all stack them all together to see Andromeda. With a short exposure time and dim objects, this is going to push you to much, much larger ISO settings. And again, the ISO settings may be camera dependent because there could be slight differences between the ISO on a Canon camera and a Nikon versus a Lumix or something like that. What I typically do is start out at about ISO 800, and then I try higher ISO levels until I finally get the level of detail that I want in the image. All the time, though, holding to this rule of 500 maximum. You do that and it works. This was an image I took right down at the bottom of the road to our house. You've got the moon. What's cool about this is it shows the orientation of the moon, Jupiter, Mars, and Saturn right there, all in one shot. And that's the kind of thing you could go back to Stellarium and look at and say, I wonder what it would look like. This image was taken at about 4 in the morning, and it was in April of, gosh, I think I had, yeah, April of 2020. But this type of image shows the alignment of planets, the moon, and everything versus what Galileo would have done with his, chalk and paper sketch of the thing. So this actually used ISO 400. Planet and constellation imaging. This is an image I took over at Fisher Towers in Utah. You guys, anybody been out to Utah lately? It's a great dark place. Look at the good stuff that's in this picture. See the belt there? That's Orion. There's Betelgeuse. See, it's kind of reddish. And let's see, the Orion Nebula should be, I think it could be right about there. A little higher, oh, right in there. But at any rate, this picture shows the orientation of a complete constellation. And this is different than Galileo with his hand-drawn sketches. This is pretty accurate. The other benefit you get is, good Lord, you got the Milky Way hanging out right back there. So this was f1.8. This is a wide angle shot, 14 millimeter lens, 15-second exposure. And here are all of the planets, or excuse me, all of the stars that were in there. Betelgeuse up there, Regal. You got the 3 stars making up the belt, Procyon, And, basically you get the whole orientation that you can match up to something you might have seen in stellarium. Constellation imaging continued. This was probably my most exotic photograph. This was of the great conjunction between Jupiter and Saturn that took place in December of 2020. And I took this about a block and a half from where I live. I went out thinking I'm going to be alone and the only one out there on this road. My God, there was like a traffic jam because it had a perfect viewing of the kind of the southwest and west. And I'm telling you, there were neighbors I didn't even know I had were all lined up there, and I kind of got there late, but I set up and played around and got this shot. You can very clearly see the rings on Saturn. You can see the stripes on Jupiter, and you see some of the 3 of the Galilean moons all in one shot. That was a half-second exposure at ISO 8000. Milky Way imaging. Milky Way is a very dim object, but the field of view basically spans the entire night sky. Some people actually go out and try and shoot the Milky Way using a fisheye lens, which gives you, the whole sky, 180 degrees. At any rate, that's your field of view. Unless you have a fisheye lens, you're not going to get the whole thing in one shot. The imaging requires a wide-angle lens, long exposure, and high ISO settings. One of the concerns is typically when you put in a very high ISO, like 10,000 or something like that, you're going to pick up a lot of sensor noise. It makes the camera sensors just kind of overreact. They're picking up noise that does not really reflect the light that's coming into the sensor panel. Again, to do this, I'm going to pre-focus the lens on infinity. This is not done with a telescope. This is just a camera with a wide-angle lens. Sturdy tripod, external shutter release. Again, turn off all the whiz-bang features. I typically use 3800 Kelvin for shooting the Milky Way. Might have a different title on another type of camera though. And again, manual shooting control. I'm again going to be using that rule of 500. Again, remembering we've got rotation of the Earth that I have to deal with. Long magnified exposures will become not only streaked. Some people like the artistry of watching, the Earth rotate and the stars, making a nice arch around things. I think I've got a picture up on the wall of that happening. But again, we're going to use this rule of 500. And applying the rule of 500 with a wide-angle lens, I can go out to about 35 seconds exposure. That compensates for the dimness of the Milky Way. With short exposures, dim objects, I need relatively large ISO settings. Again, it could be camera dependent. I typically, when I'm shooting Milky Way, I start at about 3200. And I raise it until I get the level of detail I want, but not to the point where the image is picking up a lot of, noise in the image. By noise, what it looks like, a lot of gray stuff starts to appear when you get signal noise in the sensor. This is an image I took on top of Mount Evans. I gave a copy of this to the Professor Hoffman at DU. She was impressed with it. But I went up there in the middle of the night and hiked around from the parking lot and took this, I can't remember how many years ago, 2018. The settings were about ISO 8000, 25-second exposures. Again, this was all sitting on a tripod. Now, what's cool about this is this image shows planets right there. We've got Jupiter there. The other thing is there is this leg that extends out here. It points to almost exactly to what's called the Lagoon Nebula, Messier number 8. There are more Messier objects in this because most of these features are some facet of the Milky Way. This was an image taken out at Goblin Valley in Utah. Anybody know where that is? Yep, been there. That's a phenomenally dark place. Again, you got the Milky Way here, Jupiter over here, and I believe Saturn is somewhere around there. So summarizing the basics of trying to take one shot and get a picture showing orientation of stars, planets, galaxies, and all that. What we discussed, photographs have basically replaced hand-drawn sketches. This is something that, I think if you took an astronomy course in college, they would have probably had you have a log book where you drew some sketches of the three stars in Orion's belt, and Betelgeuse is up here, and Procyon, and they basically single shots with a camera have replaced hand-drawn sketches. We talked a little bit tonight about how you make sure that your field of view is aligned with the size of the object you're trying to photograph. Solar images, I talked about the Sunny 16 rule. It works. Live it. It works. I've talked about with longer exposure photographs to avoid streaking caused by the Earth's rotation, what we call a rule of 500. And that basically you take 500, you divide it by the focal length of your lens system, and that sets the maximum time in seconds that you can have the shutter open without it turning into dashes. With that, I thought we would, at the 1 hour point, take a break, get some water, use the facilities. In the back of the room, I have brought a telescope with the full mount for rigging a camera onto it so you can see it up close. The pieces to link your camera to the telescope are not that expensive. A T-ring is about, $15. The Barlow is, maybe 30. I can't remember what Barlow's. At any rate, take a break and we'll gather at that table in the back.